Welcome back to the class of differential equations and the matrices. We are continuing to work on section 3.6, basis and dimension. Basis and the dimension, and we talk about the span. Span, it is a collection of linear combination. A span could be a subspace, and indeed a span could be the entire vector space. I hope you see that. And also one bigger thing, actually we see to some point, like an example to part A, when we add a new vector there, it will not change the span. And part B, we add a new vector there, it does change the span. Actually, it is expand the span as you may expect. Okay, so there is another concept to clarify. The span, it is a linear combination. So this W, if you noted, if you remember, this is example to part A. W, indeed, it is a linear combination of U and V. And when we see W is a linear combination of U and V, we say W it is linearly dependent on U and V. And X cannot be written as a linear combination of U and V. And then we say X is linearly independent to U and V. Okay. So indeed, the next concept I'm talking about here, it is the linear independence. And this is the concept of linear independence. And we are given a set, and if the set, any of the vectors in the set, okay, cannot be written as a linear combination of other vectors. We call this entire set is linearly independent. And then equivalently, it might be very hard if you check one by one. V1 as a linear combination of others, and V2 as a linear combination of others. And usually to check the linear independence, we are going to use this equivalent condition. And then we want to see if such a vector equation, the linear combination of all factors equal to zero, equal to a zero factor, if this linear combination of all factors has a unique solution, okay? If the system has a unique solution, actually I think I did not write down this completely. The system has a unique solution. The unique solution really means all the constants equal to zero. All the constants equal to zero. I'm trying to see if I can fill in those details quickly. It should be this part. No, I don't need this. I need this. The subscript notation part. C1 equals C2 and all the way to the end, C sub n. C sub n equals 0. If the system has a unique solution, such a solution is a trivial solution because all the numbers equal to 0. Okay. So for example, for the two-dimensional space, we know those two factors are linearly independent, and you can give a try. And you cannot write one as a linear combination. By the way, it is worth to mention, if you are considering the linear independence of two factors, basically you only need to check if one is the scalar multiple of the other. So clearly you cannot consider this as a scalar multiple of the other. So it is linearly independent. And also for the vector space of R3, the easiest one to consider the linearest independence, you are having those unit vectors, okay, in the x direction, y direction, and z direction, and they really don't mix. Or precisely, we can say they are linearly independent. They are linearly independent. Okay. And now let's take a look. Well, actually, this is a set I already mentioned. We consider set UVW. It is a set we consider in example 1 and example 2, part A. And we noted W is a linear combination of U and V. So this set, it is not linearly independent. Okay. And also, I suppose I do have another set, UVX. And we verified in part B, X is not a linear combination of U and V. So indeed, this time the set UVX, I'm saying at this part I should have put an X there. UVX. And this set, it is linearly independent because as we already verified, okay, and X cannot be written as a linear combination of U and V. And also when we check with the vector equation, as we mentioned, this is more normally we do here. So we really want to make sure, see if this vector equation is true, maybe then the only solution is the trivial solution C1, C2, C3, they are all equal to 0. And indeed it is just true. Okay, when you consider this vector equation, I hope you recognize in this case C1, C2, C3, these are the unknowns. Then according to the coefficient matrix, you are just going to put those 3 columns together. And also you can verify very quickly the determinant is not 0 for the coefficient matrix. When the determinant is not 0, then the matrix is invertible. When the matrix is invertible, the system can be solved using the inverse. And because the right-hand side is 0, which simply means C1, C2, C3, they will all have to be zeros. So indeed, in this case, we are having the set linearly independent. And also, I do have another example here. We are having set of 3 vectors. And we want to know if it is linearly independent. To make it short, I just want to know, basically, you only need to consider the matrix if the matrix, okay, formed by the vectors in the column fashion, in the columns. So indeed, this time I just said, well, I look at the determinant of the matrix formed by those 3 vectors in the column, and the determinant, it is not 0. Which means the set, okay, this set, those 3 vectors are the set is linearly independent. If the determinant is 0, which means it is not linearly independent. Sometimes we do say that's linearly dependent. So in this case, we do have the case of linearly independent here, okay, linearly independent. Okay, then I suppose you got some idea about the linear independence of vectors, and indeed the functions could be vectors too. So the next topic, it is about linear independence of functions. And indeed, if you remember this class, it really has 2 topics: differential equations and the matrices together. And if all possible, we do want to put them together, both topics, if all possible, together. So the linear independence also can be applied to functions. And when you have functions as vectors, so accordingly, to check the linear independence, you want to check this equation equal to 0. If it only has a trivial solution, which means all the c is equal to 0. Okay. So the next example, it is from the example 10 from the textbook. We want to check the linear independence of those 3 functions. First of all, they do look different, right? But anyway, mathematically, we want to describe them more accurately. We want to see if they are linearly independent. So according to what we just stated, we are having three functions. So we want to check this vector equation involving with functions. Replace v1 with e to the t, for v2 with e to the negative t, and v3 with e to the 3t. So indeed, we want to check if this is a system. Indeed, it could be a system. It should be a system. Okay, we'll see in a moment. Okay, replace v1 with e to the t, v2 as 5 times e to the negative t, then v3 do the same thing. Okay, and we want to check if this equation only has the trivial solution c1, c2, c3 equals 0. And then what I did here is because we really want to make sure this equation would be true for any value of t. And just to make sure it is true for any value of t, I chose some special values, some specific values you choose, and make some simple and easy choice if all possible. So what I decided here is what would happen to this equation when t is chosen 0. So I'm having e to the 0, that's 1. Then 5 times e to the 0 is 5. E to the 0 again, it is 0 here. It is 1. So the first equation. And simply from the first equation, you cannot solve the system. You cannot solve C1, C2, C3. So I chose another two values for t. T equals 1. Hopefully, I think I should be fine with all the numbers. And also I chose t equals negative 1. Now, as I'm saying, the vector equation really represents a system. So I figured out this vector equation has a system implied. Okay, and then for the system, it may look very much complicated, but if you know the matrix multiplication, it always can be considered determinant matrix times the C1, C2, C3 in the column fashion. So I did write out a determinant here. And also, you may want to give a try to see if you can calculate the determinant. And my calculation tells me the determinant cannot be 0 at all, not close to 0 at all, which really means the coefficient matrix, it is invertible. So accordingly, we can find out C1, C2, C3 using the inverse multiplied to the left of the column vector 0. Which really means C1, C2, C3, they will all have to be zeros. So accordingly, it simply means those three functions, they are linearly independent. Because this vector equation only has a trivial solution. And if you are not sure why we have this vector equation, consider this arrangement. And it tends to be system. And even for those three specific choices of t, the system only has a trivial solution. But anyway, the system really will have to be true for all t values. So indeed, C1, C2, C3 must be all zeros. And I said that the conclusion here is those three functions must be linearly independent. Thank you for watching.